Okay, so let's look at the Predator-Prey model. So the Predator-Prey model is a little bit different than what we have done as competition. And in this model, we're going to look at two groups, of course, the same way we did before. And so one group is predator, the other is prey, and how these two, the population of these two affecting each other. So that's what we're going to look at in this one. Okay. Uh, yeah. So let's get started. I think there are a few terms. Actually, it's not many as before. So, what is predation actually? And that's where we're going to start talking about the rest. Okay. So, so what is predation is the interaction actually between two groups. One group we call predators, the other has prey. So yeah, uh, so how their interactions cost their population. That's what we're going to look at here, right? For the example, on this book, they have given you the interaction between hogs, right? Hogs and squirrels. So these are the two types that we're going to look at in this example, right? So what are the assumptions we have to make in this case, right? So the assumption will be, well, hogs eat only squirrels, right? So only so that this case actually the hogs is there. So this is a hog, right? So their only food source is these little squirrels here, right? So that's what we had to assume, but it is not the case, right? The nature, well, uh, you will have more than one food source, of course, for an animal. But we assume that in the previous one as well, the limited resources, or we'd say, well, this is only one kind of fish group, right? So the last competition thing. And here as well, so we are thinking, we assuming that if there are no squirrels, no food for hogs, right? So the concept behind this actually is pretty important for you to know. Is all right. So if you have um, more squirrels, right, and so that means the hogs has enough food, so they don't have to fly far away. They know where the squirrels are, so whenever they're hungry, they can come and eat them, right? So in that case, when that happens, yeah, the hogs are very happy. Um, they are um, uh, they are very happy because they have enough food to survive. So they have uh, they don't have to spend a lot of time on food. So they're the same case like the previous one in the competition. In this case as well, the hoax population will grow, right? So because they have enough resources, they don't have to spend more time on that, so they will manage their life better, right? So then, so the if they have enough food, which means nothing but uh, uh, the hogs, their population goes up. So their population, the hogs population goes up, and so then they eat more and more squirrels, right? So when they eat more and more squirrels, well, the squirrels population, well, goes down, right? So then the hogs will be more hogs now. Instead of few, there are more now, right? And so that will cause a problem to the squirrels. So the squirrels population goes down. When the population of squirrels goes down, hogs don't have food, right? Why? Well, we assume at the beginning that the hogs can eat only squirrels, they're nothing else, right? So in this case, that's a problem, right? So when they are going down on the population of the food source, again the squirrel, I mean the hawks, has to fly away and find food, so they have to spend a lot of time. If there are weak hawks, they will die and things like that. So what happened again? So again, in that case, when the situation is like that, hawks population, right? So let's say this is the hawks population. Well, that goes down. So when the hawks population goes down, so what happen is, well, now the death rate of squirrels is less because they are um, uh, they can survive more now because no are predators. So their populations again going to grow up, right? So when this population grows up again, right, uh, the hawks has enough food again, right? So now there are more squirrels here, happy life because they don't have much more predators, they don't get attacked as often as before again. So their population goes up, right? So their population goes up and the hawks coming down. Then again, hawks have enough food, so because they have so many preys now, and it will shift into this situation again. So it will go on a cycle like this, right? And on. This is going to be exchange each other, right? So that is the concept that we're looking at in here, um, which is in some period of time, predators population is high. Whenever it's getting high, the preys are going down. When the preys are going up, when the predator is not a threat as much as they think. So it's like that. So it's going vice versa, right? So that's an interesting concept. So we're going to look at on this. So this model is called Lotka-Volterra model. So the mathematicians in 1920s, the Vito Volterra and Alfred Lotka, those are two mathematicians actually. Well, the computer science was not exist or anything else. So the mathematicians are the ones, the pioneers of modeling and things like that a long time ago. Uh, so these are the ones who proposed this model, and so we are looking at the example of hawks versus squirrel population in a certain area. So remember the name, Lotka-Volterra model. So that's what we're going to look at. Okay, right, and so yeah, before we move on further, there are a few things that we had to address here. I mean, these are not in the chapter as in the beginning of the chapter. These are some stuff. One part is in the beginning, the other is at the end. So I just put it there just to just for you to know. Can prey become a predator? Oh well, the answer is yes. They have a good example here about the poison dart frog. That's a little frog. Well, and whenever the predator comes to attack them, the problem here is these frogs has toxic skin. It is alkaloid chemicals in their skin, and they are very colorful, and so it is very bright, and anybody can see them. They don't have to. They don't actually camouflage themselves like the other prey groups. In this case, whoever attacks them either get paralyzed or they killed by the toxic, right? But they don't eat them, so in that case, they are not predators. They are prey because they get attacked, right? And well, in this case, I don't think the frog is surviving either. Maybe, I don't know, but because it's a skin is the only thing toxic. So whenever predator come and grab them, they get injured as well, I guess. But anyway, So predators die by attacking this kind of prey is kind of a backfiring the situation, right? So that is one thing that we have a gray area between a prey and predator. So the predator is always dying by attacking the prey. That is the interesting part that you may aware of. I mean, we should be aware of. There's certain gray areas like that. The other one, why we studying this model? Well, this is something about the war between hogs and squirrels. Why do we care, right? Yeah, that is a good question to think. Well, so the reason is, well, this nature is balanced, right? And there are few things that are very important for you to know. So if you take off one part, that causing a problem to the other. So this is the example is given by the historical nodes here, the revolution time in China. So what happened is, well, the Mao is the one who controlling by then, and well, they look at what's going on. I mean, they run out for food and everything. So then the farmers comes and said they have to give an excuse what's going on. So they said, well, these birds comes and killed our crop. So that's what the problem. So because of that, we cannot produce enough, right? So there are some birds. So then the Mao ordered, okay, kill the birds. So then we can have enough food. We can have the crop. So there were no studies about anything like this. So what happened is they went and then they killed more birds. So the after effect of that is when they kill the birds, the prey, the part of this ecology is insects versus birds are the predators. So they kill the predators, and then the insect population start to increase, right? So that is more harm for the crop than just the bird did. So we can see, it's very important to study these kind of things before you do an action, right? So this is what a good example that I can provide, which is provided by the book, saying, okay, so you, if you try to take off the balance in the nature by destroying one type, which is a predator group in this case, and the prey get more powerful, and the prey get powerful, and then the disaster is much more than before, right? Yeah. So why? Well, the birds actually eating those insects, so they keep the insects in control. Because of that, crops survive more than when the insects start eating the crop, right? Okay, so I hope you understand the depth of that and the importance of learning this part, right? Okay, so let's move on. Right, so we recall something from the previous lectures here. So we base on this whole thing is based on population. So what we know about population is again directly proportional to the initial population, and we know that the initial population, I can write it as the previous time population. So this is the symbol, I mean the knots we're going to use. So this is what the previous population, right? Previous, right? Previous population. So this is what it is, right? Right. So that is what we're going to use here as well. The previous population and the current population is proportional to the previous, so that means we need a constant here. So instead of this one, I'm going to write with this, so you can write the population is equal to constant time, and here we're going to use k constant times as t minus delta t. So we know this one already, right? So keep this one in mind when we're looking at this one, right? Okay, so let's put this on the side. All right. And what else we know? We know the change in population. So this is what change in population is, right? Is equivalent to the current population. This is the current population right here minus the previous population right here. Okay, so that is something that we know by what is this called? Difference, uh, finite difference equation, right? So this one we call finite difference equation. Change in the value is equal to new value minus old value. So that is a finite difference equation, right? So that's why I ask you that in the exams as well. Now you know, right, why those questions were there, right? Okay, so this is the same thing when we writing it in the other way, which is this one, the change in population. So actually what I have to say here is this is the change of rate, which is actually proportional. So we have these parts, even I did not write it there. So this is actually the change rate, right? On the other hand, I can write this as a delta S over delta T, right, is equal to constant time previous population. So this is what actual equation is, right? So this is yeah, give me a second. So this is the actual equation is, right, like this. Okay. Okay, so well, that part we already know, right? So this means the change in population is nothing but equivalent to something at something like this right here, right? So this means delta S, I'm taking the delta T onto the other side. It's a constant. We're talking about the squirrel population here. So this is the squirrels. We call the squirrels as S, right? And and then the previous squirrel population is T minus T minus delta T, right? And then since the delta T on the other side, so I can write that one here like this. Okay, right? And so this is what we're looking at right here, right? So it's the same equation. Okay, so well, this is so this is what if you don't have any influence of any other creatures, and how we consider the change in population equation. So that's what it is, right? Okay, so we're going to model this starting there, and it will be a little bit complex when it's move on. So pay attention, and then we'll see how we're going to model this. What are the equations we're going to use? Okay, right. So then, if there are no hawks, this is what's going to happen, right? But we have to apply deaths into this, right? So if there are no hawks, this is what we have. If there are no hawks, we are just having the birth. We are applying the birth only in this case. This is unconstrained. We consider that we did not apply the deaths yet. We saying okay. So if there are no deaths, we consider they are live for months and months. So don't worry about any deaths here. But when there are hawks, of course, there's a threat for the deaths, right? So the death has more impact now. Why? Because the hawks come and kill them. They kill the young squirrels as well as the old ones. The mostly young ones. So the population get a huge impact, right? Because their reproduction goes down when they're attacked by the hawks and kill the young squirrels. So that is important. So because of that, we say the population. So that means if you have more hawks, so instead of one hawk, if there are two or three or four, the number of squirrels get attacked is high, right? So that means what? That means the hoax population also matters to the death of the squirrels, right? Right. So that's what the conclusion here. The point here they just point out what is the death or the reduced amount is going to be. Okay. So the population is reduced by amount. So the reduced amount of the population, right? So this is like the deaths, right? So you can say reduced amount, change of deaths, right? Okay, is proportional, so it is not equal, actually it is proportional. So you have this little symbol here, right? Proportional. Yeah, it's proportional to the product of number of hawks and the number of squirrels. So the number of hawks, number of squirrels. So this is the number of hawks the previous, and this is the number of squirrels previous, right? You know what is t minus delta t means, right? So if the current time is now t minus delta t means the previous time. So it is we talking about one delta time interval before, maybe the last month. In this case, I think it's month by month. They just creating this, the simulation. So in this case, delta t is 1 month, right? So it's a 1 month before we are looking at right now. So we go and get the statistics 1 month before, how many hawks were there and how many squirrels were there. And then after 1 month, today, just after 1 month, I come and look at how many crows are there, how many hogs are there. So there's a total different population values are there. So you take those. So like that, you can collect the statistics and come up with some equations. So that's what this whole model is doing, right? So then, of course, if you have the proportionality like this, you can apply a constant. So this is what we call proportionality constant, right? So in that case, the delta d, right, you can say equal in this case, right? Instead of this, now I can put this because I applied the constant value, right? Reduced amount is say k hawks and squirrels. So it's like hawks, squirrels, right? So pay attention on this one as well. So this is changing from hawks, squirrels to hawks, right? So oops, I jump one head. Okay, so this is what the depth value is going to be, right? So this is nothing but the depth value. So now we're going to apply the depths into our equation, right? So how do you do that? Well, the previously I had only the births. So this is the birth part. So this is we call births, right? Births. So we had this before. We call this births. Now I had to apply deaths as well. So this is the remainder of the population now, right? Yeah. So when you reduce the death. So how do I reduce the death here? Well, the death is given by this equation right here, which is the same thing right here, right? We came up with using this concept up there. All right. So now the births minus death is the remaining population into delta t as we put it this part right here to here, right? So only change here is instead of initial population, now we have initial population defined by the births minus deaths. So that's the only thing in there, right? So this is a one example of this equation right here, okay? And the adding the change in population, right? So this is actually if you have this is a change in population means actually this is not delta S here. This is the deaths that we're calculating here, okay? Let me see if that's the case. Yeah, no, I'm sorry, I'm taking it back. So this is what actually this equation right here, so not this one. So right, so this is the equation. Okay, so this equation example is right here. So if I have three hawks and two squirrels, right, and the change in population will be equal to this is the starting birth or whatever the previous population of squirrels multiplied by its constant, right? And then this is the part we are talking about right here, right? So this is the constant times the population of hawks and the population of uh, uh, squirrels, right? So you multiply those two, and then the whole thing multiplied by delta t, which is this one right here, right? So this is the same delta t, right? So the equation is equal to 2ks minus 6 because of the total population into khs multiplied by delta t. You may remember thumbs of rule of thumbs from the previous lecture that we were talking about. This khs has to be less than 1, right? Why? Well, if it is increased more, doesn't make any sense for the population unless this k is really big, right? So you may remember in competition, you can go back and look at it. Um, we had the death constant actually is a point something always, right? Most of the times. It's not always, right? So when you're talking about millions of people, you cannot say it's less than 1, but it will be 1 decimal to the left. So that's what we were talking about in the previous lecture. You can go and check it on that. So if you have, yeah, it's in the very small number like 6 or something like that, it has to be less than 1. But if it is you're talking about millions, of course, you may have to consider this one as different values, of course, right? uh, right, so let's move on. So now the funny thing in this equation is well, this is for the squirrels. When it comes to hogs, it will be the other way around, right? So that is the one thing that you had to notice here. um, when it comes to the hogs, we're going to reverse this equation, right? So while the squirrel population decreases more, right, what happens when you having a more food to eat? Well, then the hogs population will go down, right? Yeah. um, so and then what happens is as I said before, so if you have more squirrels to eat, right, and so the hogs comes and eat them, right? So these are the hogs comes and eat them, right? So they have fat belly because they have enough food, right? Okay, so now they're eating a lot of them, right? So what does this means? This means when they're eating them means their population goes down, right? Again, eating has more food means their population goes up, right? So while this is going down, this is going up. So that's what it means, right? That's what it means by this sentence. When you're looking at it, it doesn't make any sense, but that's what actually happening here is during the time this population goes down, during the time the squirrels population goes down, right? The squirrels population goes down, the hogs population goes up, and then at one point this is going to be a reverse. Why? When they don't have enough food, well, they start dying. So when they start dying, I mean the hogs start dying, the squirrel population will be increased. So this is how it's going vice versa, right? Okay, so because of that, at the beginning we consider the change of hogs population is the hoax population, initially the current hoax population minus the previous hoax population. What is this? This is the finite difference equation. This is the new value minus old value, right? Is the change of population, right? And here, when we applying the equation, so the new value here is we consider as this right here, right? And this is the old value, which is the previous time. So this is the previous time hoax population, and this is the current time, the new value, which we're going to take as KSH. So you can see the previous one we has HS, now we have SH multiplied by the hoax and the squirrels. So the multiplication of those two populations are here. Subtract the previous one will be the change in population. So that is the twist from previous equation to this equation, right? So these are predators model. So the predators have this kind of behavior on their change in population, right? And but the prey has its reversed, right? So those are the things very important to notice, and of course, and this one and this one as well. Okay, so let's move on. I hope you understand this concept. And then what Volterra model, what is proposing there is, you can notice here on this equation for the preys. So these guys are the preys, right? In the preys you have the population minus the death right here, multiplied by delta t. So this pattern is for the preys, right? The product of the population is coming to the second. So this is the subtract the product of population. If you have the product of population at the beginning and the previous population afterwards, so this is actually the predator, right? This is the predator. So make sure you understand that. So that's what I'm going to test you actually, whether you can understand by looking at these equations. I would give you these equations in your exams as well, and identify which one is predator, which one is prey. So you're looking at these two terms here, and which one is subtracting by which will tell you which one is prey, which one is predator. Right, so this is the differential equation for this, the same thing, right? So it is a shorthand writing, so you can look at this one. You can see it is a short way of write the same thing using a ds and dt instead of delta s and delta h or delta t. Okay, so you can write it like this as well as so the both ways it's saying the same thing, right? Okay, so very important for you to know which one is prey and identify which one is prey and which is predator. Okay, in this case, so this is what we call Volterra model, and this is the model we're going to simulate putting into the VanSim actually, right? So so these are the example questions I would give you, right? So what is this one? Okay, so you have delta x and delta y. You don't know what those are, right? And asking, consider the differential equation given to you, and it's asking which one is the predator, right? Which one is the predator population? So how do I identify the predator population? Well, from the previous slide I told you, you look at this product, right? In this one I have the product after subtraction, so which is right here. Okay, and so well, we know if we having it in the front, so that is the predator, right? So the predator is this guy right here, right? So that's how you identify that. Okay, so if you know that part, we'll know what is the death fraction and what is the the birth fraction, right? So we know that already. So this is the death part right here, and this is the birth part right here. So we know that birth minus death only for the prey, the predator is the other way around, right? So in this case, the second question, second question asks the number of representation of the predator birth fraction. So what is the birth fraction? In this case, the births minus deaths is always like that. So it is this guy right here is the birth fraction, right? And the number of representing the prey birth fraction is always like this. So it is always the birth minus death. So that is how we say change of population is always equal to birth minus death, right? So in this case, whatever you have in the front is what the birth fractions are, right? What you have in the second part is are the death fractions. Okay, so in this case, so let's we did this one, so it is 0.001. If you know what is the predator is, you know what is the birth fraction of that, and the which number represent the prey fraction. The prey is the first one, and the birth part is that right there, and the death proportionality of the predator is actually this one right here, right? So because it's birth minus death, so it is this one right here, and the number of representing death proportionality constant for the prey is right here, right? So because the death is the one which is coming at the end, so that is that. And what is the initial number of predators in this case? I'll say the y0 is the predator part is 15, so it is 15, and then for the prey equation the initial value is 100, so it is 100 right here. So that's how you analyze this equation and come up with the values. So you have to keep in mind this concept right here, right? Always a change in population is equal to birth minus death. That is a one way of looking at it, right? So make sure you understand that. Okay, so let's move on. Right, so these are the equations. You can draw this in Vensim for the practice if you like, and plug in those equations I have given you here. These are the only equations you need in order to come up with the final result. So let's analyze this a little. So you have birth fraction and to the birth, so this is that part right here, right? So if you consider this one, if you are no death, so the unconstrained model, you have your which is dp over dt is equal to constant time, right? So this is the constant time, which is a birth fraction. So let's say let's put something here like r or something like that, multiplied by the previous population, so it is s t minus delta t, right? So this is what you apply in your equation to the Vensim. So this is what actually it means, right? So then here the deaths are here. So in this death equation we have different values because we are considering the population of this one multiplied by this. So that is what we have in let's say this side is prey, right? This is a prey bird. So the death of prey is like this. So this is the equation for this. So this is the equation goes to this guy right here, right? Prey deaths. Okay, and if you are writing it in the equations like this on for your final report, this is how you model this equation. So that's why I just wrote it up there. right? So this is births minus deaths, births minus deaths equal this guy, right? So this is, that's why it's in the middle, births minus deaths right here. Okay, so then so you can see births minus deaths, so there's a death rate and then the birth rate. The difference of this will be the population in the middle. Okay, and of course I say the population, the deaths of this matters by the population of the other, so that's why this arrow is going right here. Okay, and then also then also the population of this matters to the births of the other, so that is this arrow right here, right? So why is that? Well, you can see the equation for the predator birth, right? Predator birth, which is the birth fraction of the predator. The birth fraction of the predator matters by the population of prey multiplied by the population of predator as well, right? So that's what we came up with the equation before. Um, if I recall, I guess I was talking about that. 1 minute, right here. Yeah. So so this one right here is for the predators. This is the birth fraction, which is depending on the squirrels as well, right? So the squirrels population matters to the birth of hogs, as I think I can remember that I talk about that. So that's why I'm just pointing out here again. So make sure if I did miss talking about that, the hogs population or the predators population is matters by multiplication of those two products. On the praise, on the other hand, in the praise, this product matters to depth of praise. So that's the difference. Okay, right. So let's move on. We did this. We were looking at this. So that's why I would say the praise population matters to the births. So the praise population matters to the births of the predator, right? And then the deaths has nothing to do with it, so that's why there's no arrows from there to here. And so this is the connection on these dark black arrows are the connection between the population relationship between the prey and predator, right? So this is how you model this. I believe you understand. If it is not, you can ask questions in. I'm actually going to post this in the YouTube. So in that case, there is a comment area open for you. If you can comment on that, or you can send me email or contact me through Canvas, or either way. So you have enough ways to contact me if you really struggling to understand this. Okay, right, so let's move on to the next one. So see how the graph look like. So I encourage you to put these equations and draw this in Vensim and see whether you can come up with the same equation or the same graph, right? So that is important. If you do practice a little bit of those, you get to go with your own simulation, right? So that's what the one part of this course encourage you to do and make you doing. Right, so this is how it look like. So you can see it's pretty interesting, the behavior of this graph right here, right? So you can see the predators are the dark line and the preys are the dot line. So you can see it's balancing each other. If you have more of these, you have more of these, right? So if it's going down, well, if you're going down, well, of course the predator is going down as well. And again, when the predator is going down, the prey is going up. So the predator is going down, prey is going up, like that. And then again, the preys reach some point, so then the predators going up again. So it's very interesting way how it's the ecology behave and the balance is maintained. And again, when the prey is going down, after a while, then the predator is going down. So it will go up and down like this. So these, if you break one of these links, the other one will go up and up and up and up. So this is where causing more problems, because this will kill the balance of the nature, right? So in that case, uh, the one part will go. That is what happened to the bugs versus birds, the situation on the crops that we were looking at. So this is actually the table after you model this, right? So this is talking about months actually, and then each month we calculate the population, right? So this is how it's looked like. So the next graph is pretty interesting. I'd like to point out a few things on that if you having a hard time understanding this. So here, well, you can look at this one right here, right? So this is the predators and the prey, and it says the time going clockwise. So think like this. It's very hard to analyze this one, but if you're looking at it very carefully, you can understand what is going on here. So here it says 15 and 100. So the predators are 15 somewhere there. Let's say this is 15, right? Let's say this is 15, and the prey is 100. So let's say somewhere here 100. Okay. So what happened here is you moving on. So whenever you're moving on, so this is, so it's less hogs, right? So if there are less hogs, well, the what happened is, if there are less hogs, these guys, which is prey, or the squirrels, increase their population. So nobody to attack them much. So their population grows and grows and grows. And there, whenever that happened, gradually, the hogs also uh, increasing. Why? Because they have enough food, right? So you can see now those are increasing too. So once when it is come to that level of break even here, so that happen is, well, you have enough food now, right? So you have enough food. So the hogs are increased up to this level. Now they are going to attack the squirrels. So when they are attacking the squirrels, because they're getting hungry more and more people, more food they need, then these people again reducing their population. So what this means is it's going backward, right? So now it's going backward. Why? The hogs are going upward, and then this one is going down. So the population again decreasing once when the population of hogs going up and up, the preys, which is the squirrels, going getting less and less. So this is the comparison between predators and the prey. So you can see now it's come to here. When it's come to here means you have less amount of squirrels. So it's 100 versus about 375 or 350, let's say, right? Here 350, let's say, right? So now when it comes to that, 350 versus 100 is a very less food source. So in that case, it will coming down again. So now there are not much food, not much the squirrels either, because they're still eating them, and so then the population goes down and down and down. And again, when it comes to here, this area, the population of hogs are less now, and so the population of squirrels increasing. So it's like this is a circle, it's a cycle is going on. It's pretty interesting way when the graph, when you're looking at it, when you at glance you may get confused, what in the world is this, right? So now I think you have a little idea what it is, right? So in this case, on the bottom part here, they are plugging different initial values. So these are different initial values, the starting values are different, and see how the graph behaves. So you can see this is not good way of writing the colors here. It says black, gray, and the dark color and the light color. Oh well, I think they have looking at the black and white when you're writing this. It's not a blue in it, so it's only black and gray they're talking about, I guess that's what it is. Otherwise, they should have put blue and then a light, whatever it is. Right. So I think these two are talking about the initial value of 15 predators. Right. That is the first graph right here. This is the first one which is talking about here. And so anyway, so this is the one that is showing you here is nothing but this one right here. Okay, but the colors are messed up, so that's where it's leading the confusion here: light colors, dark colors, and all that. But anyway, I hope you understand this graph right here, right, and the behavior of that. Okay, and yeah, so I think that is all for this. So make sure you understand the equation. So what are the most important part in this one is actually these equations and these questions. Okay, so make sure you understand these questions, how to answer those. Those are the ones will be on the quizzes and the exams. And if I give open book quizzes, I might consider your understanding more than memorizing things. So make sure you understand more than just try to memorize the answers or having a short notes. Okay, right. Okay, so this is a lecture on Predator-Prey. So we're looking at the malaria and the SARS and how you model those on the next chapters. And right, so I will keep posting, and you can go over and over on the same video and study. Right? Okay, we'll see you in the next lecture.